Good afternoon, everyone, and welcome to this edition of the Liver Seminars. Today we have our guest is Tom Lude. I met Tom in Aachen during my postdoc in Germany, and he's very well worldwide recognized medical doctor and also researcher. He has a very long experience as a postdoc in Rome, in the United States. And then he returned to Germany, to Aachen, where he started his medical career, but very focused on research. He's very well known because of the Nemo mice that you probably have heard about. And now he's currently the director of gastroenterology, hepatology, and infectious diseases in Düsseldorf hospital. So he's now focused on cell death, and I think his contribution today is very important for the hepatology field because it's a trending topic and we need to know more tools to define cell death, no? So the title of his talk is Cell Death in Chronic Liver Disease. So I invite Tom to come here and start whenever he's ready.
Thank you very much. First of all, thanks for this very kind invitation. I'm very happy to be here. I must say I'm also very impressed of this place and of the work I got to learn today in Javier Cubero's group with fantastic science, fantastic students, and also I learned that this is really a network event with many colleagues also from other places in Spain. I warmly welcome you. And it's a great pleasure to be here and speak about a topic that is, in fact, at the heart of my interest. And, when I like speaking about cell death and when I come to new places like here in Madrid, I tend to type in the words death and Madrid in this case, And I came across this fantastic picture that is here, obviously, in the Prado Museum. It's called the Triumph of Death. So maybe tomorrow morning I might try to sneak into Prado Museum. The Triumph of Death, it's a little bit, also, it's not a triumph, but we're still quite happy that we started to work on cell death now almost 20 years ago. Here, Madrid is also a very important place for me because it was in El Escorial. I attended a meeting in 2009 where luckily I got across the concept of necroptosis, which was first shown by Vishwa Dixit at that very conference. And since then, we got really interested to study the concept of programmed cell death. So I start with a picture. I learned there's also medical doctors in the crowd, so I start with a quick medical introduction, and also so for the biologists or scientists here, I think you guys are working very translational. This is a picture of a patient back in Aachen that I treated. 40-year-old patient came with discrete abdominal pain, no alcohol history, but he was a bit obese, very mild lab elevations, but then on ultrasound, we saw the mess, and this is a PET scan that we normally don't do in liver cancer, but in this case, you see here this multilocular cancer. And we were fighting for, I think, 4 years before this patient unfortunately deceased. And this is a picture of the tumor. You see on the left side, this is the picture of a typical HCC. And then this is something that we're all involved in, that we are interested in, the typical picture of a NASH, like a steatosis. So, and you see pathologists see much not easier than I see it, but like Thomas Longerich, friend pathologist, said, so this is a typical picture of necroinflammation. So obviously there is a lot of cell death and inflammation going on around this tumor. Now this is a picture here of that you know very well. I'm showing this again because we have the unique chance to identify risk populations, as you see here, from steatosis, which is probably still the major condition that in the end can lead to liver cancer. Now here, And here, this is where we would like to understand what is triggering the path towards cell death. And this is very important. This is, because I'm here in Spain, I'm showing, of course, the Barcelona treatment algorithm for liver cancer, which is great but kind of complex. And we made a lot of advances here in the systemic therapy, but still many people die of cancer. So what can we do to lower the mortality of liver cancer as a whole? I like showing this statement from Bert Vogelstein. This accounts for many cancers. The greatest potential lies in the early detection and prevention and not the treatment of liver cancer. And we've shown this in colon cancer now. And I think gastroenterology and hepatology as a topic is more and more becoming a cancer prevention topic. You know, we're doing colonoscopies to prevent gut cancer, but we have the chance to prevent and early detect liver cancer in patients with NAFLD, for example. So why is cell death important? I showed you the picture of the cell death in this NASH tumor surrounding. Now, the problem with NASH is that in the end, very few NAFLD patients develop liver cancer, right? It's not like in hepatitis C patients, hepatitis C cirrhosis with 3% of cancers per year. Here, this is one of the very important studies published in gastroenterology. You see here in 10 years, this is, I think, let's say, or here in 10 years, 1.8% in 10 years. You know, so how can we identify better those with the major risk for liver cancer? And this is a guy from my department, Sven Losen, and he studied a score. You know, this is called the FIB-4 score. It's a very easy score to do a risk assessment. I show you how it's calculated. And he showed that if you take 30,000 NAFLD patients, this is a massive number, you know, where he calculated this score. And he was showing that if the score is lower than 1.3, there is a 0% of liver cancer development within 5 years. So the negative predictive value for this score, FIB-4, is extremely nice. And if you're beyond 1.3, then the risk rises dramatically. This is a very nice tool for general practitioners to identify the patients and send them now here to Madrid for a better workup, or to Barcelona, or to the big centers. Now, what is FIB-4? It's very easy. It's age, platelets, we discussed platelets today, and then there's AST, and by square, ALT. So two of these four markers are cell death markers. So if you have cell death going on, your risk of liver cancer development rises dramatically. And if there's no cell death occurring, you're safe. So cell death appears to be a major driver. Now, what is cell death? And we really discussed in many nice projects you showed me today. You were looking at apoptosis. And when we started, Javier and I guess we started more or less the same time. This is a bit hard to see here, don't have to look. So apoptosis was the same as programmed cell death. You know, if you ask your biochemical teachers, they would say, what is apoptosis? It's programmed cell death, and vice versa. And apoptosis is a very important form of programmed cell death. I'm just quickly showing this. We have, in Javier's group, and then we have worked a lot on apoptosis checkpoints on the way towards cancer. These are the NEMO mice here. When you take out NEMO from this molecule from a liver cell, you trigger apoptosis, and this is enough to make cancer. And also recently we identified a second point here. RIP kinase 2, TRAF2 is also a very important cancer checkpoint. So these are all apoptosis studies we did. I want to point out one important thing also for the students here. You have to look at your data. I did not really look at my data then. You know, this was 2007, 2 years before my Elias Corial experience. And we were blocking apoptosis in these mice, and the mice were not completely saved. You know, look here. 200 ALT is not normal. They did not develop cancer. So there must be something else in these pathways than only apoptosis signaling. At that point, we thought, okay, it's easy. Dying hepatocytes release dumps, damage-associated molecular patterns. This can be anything that is normally not exposed to the outside of a cell, like DNA, cytokines, or whatever. And this then triggers immune cells, proliferation, genetic stress, and finally HCC. That's the model why we get liver cancer when we have cell death. But then, how about apoptosis in NASH? This is a staining, caspase-3 staining, from a very famous paper in 2003 claiming that apoptosis is occurring in NASH. So it's easy to say, right, that this is not a specific staining, right? Every cell is positive. So I think this antibody here has some problems, probably in a steatosis background. But this company launched an anti-apoptosis trial based on these stainings here and had to learn that it was not working. You know, I cannot say that apoptosis has no role in NASH. I don't really see it in our models, but anyway, this is at least something, there must be something else. And we kind of got there when we deleted this molecule here, TAC1. We saw tumors, because TAC1 is upstream of NEMO, right? So we thought we should see the same. We saw apoptosis. Then we thought tunnel is specific for apoptosis. But then we saw something. Look at these necrosis areas here. And this we had not seen in the NEMO mice. And again, we didn't know what it is. And then in 2009, we came here to LS Corial. Vishwa Dixit said there is programmed necrosis occurring. Because this is kind of the definition of programmed cell death. It's pathway mediated. You take out a molecule and then you trigger it. So necrosis can be programmed. Now we know, this is now the current situation, we know there is several forms of cell death. Apoptosis, necroptosis is kind of kinase dependent, caspase or kinase controlled, and pyroptosis you have heard about, I guess, gastroamines and all these things. And then there is ferroptosis, there's other forms too, netosis, and many forms now. It's a fantastic field. It's so interesting to see which liver disease, and this we have been discussing with Javier's group all day basically, or in many projects, what kind of liver disease triggers which form of cell death or cell stress, and which form, how do these cell death forms then act towards inflammation. This is, I think, for us, the fundamental question we want to work on. Remember this necrosis thing. We believe that in NASH, programmed necrosis might be important, and there have been papers from our group, but also from, thank God, some other groups confirmed it, that metabolic liver disease and also alcohol. There's also, this is from Cecilia Rodriguez, very nice paper on necroptosis in NASH, but also alcoholic liver disease, NASH is probably important. From Laura Nagy, there's a paper on that. Now, this is necroptosis. It's occurring downstream of the receptor. This is the only pathway I'm showing, and this is a very well-educated audience, so I can kind of briefly introduce it. TNF receptor signaling to this molecule, RIP kinase 1. This is a very interesting molecule. I could speak all day about it. It has multiple regulation levels. It can be phosphorylated to activate it. It can be phosphorylated to suppress it, and many other forms, ubiquitinated and so on. But this is a very important kinase, and for necroptosis, then you activate RIP kinase 3. From our point of view, there is no necroptosis without RIP kinase 3. Some people say there is. This phosphorylates this molecule MLKL. And then people say it's oligomerizing and building pores in the membrane where ions can flux in. But I can tell you, nobody has shown these pores yet. So there's something else going on, and I'll get back to that at the end of my talk. Now, you see here the many molecules controlling RIP kinase 1. Here, this is TAC1. There is other molecule, and TAC1 suppresses RIP kinase 1. There is other molecules like TRAF2 suppressing this, and I'm not going into details here. All I'm telling you is we used these suppressing molecules to study one important question that I will speak about today. What is the pathway doing in hepatocytes? What is it doing in liver cells? And we were looking for a way to chronically activate necroptosis and to see what happens with a hepatocyte that activates necroptosis. And this is what I'm speaking today. So you don't have to worry so much about how we did that. I try to explain it. We started again with this TAC1 mice, remember? TAC1 suppresses RIP kinase 1 through phosphorylation, and TAC1 activates NF-κB. So to study pure necroptosis, we had to take out TAC1 and had to take out caspase 8 together. And then we thought we get pure necroptosis, and okay, NF-κB would be blocked in these cells. And this is how this pure necroptosis looked like. Very funny. Necrosis, but no inflammation, no proliferation. We thought in the textbook necrosis makes inflammation more than apoptosis normally, like myocardial infarction and so on. But here, nothing. Completely unreactive. No cancer. It even prevented cancer. So is necrosis an anti-cancer thing? That was the question. So we are working with these Cre-Lox mice. You see here liver parenchymal cell LPC knockout. This is how we call these mice. They are only knocked out in hepatocytes and cholangiocytes. You call it delta hep, I think, right? It's the same mouse. And then this is all the work I want to acknowledge here from the beginning on Michael Wukur's work that we have been colleagues since like 15 years or so. Most of this work is done by Michael together with our collaborators. So one phase of necroptosis is this hyperreactive form. But then, with a different approach, we take out not TAC1, but another suppressor, TRAF2, we get a completely the opposite phase of necroptosis. Look at this liver here. And you are experts in liver, so you might acknowledge that only the center of the liver still looks normal. There is an explosion of the non-parenchymal niche of every cell. In fact, in this liver, every cell proliferates. Every immune cell, every stellate cell, every hepatocyte, every cholangiocyte. This is when you do a Ki-67, every cell proliferates. You get massive fibrosis and you get these tumors here. So two phases of the same pathway, hyporeactive necroptosis and hyperreactive necroptosis. Of course, we were completely flashed by the question, what is these two phases of necroptosis? How can we find out how this is done? So how we triggered this again, I told you, TRAF2 suppresses RIP kinase 1. It also suppresses NF-κB. So in this case, we did the very same thing. take out caspase-8 and TRAF2 to get this phenotype. And this phenotype, this is a bit larger how it looks. So the center looks, there's hepatocytes, and here, this is normally what you find, these few cells in the portal areas, they are overgrowing the whole liver. Monocytes, T cells, B cells, everything. And this leads to cancer. When we have a new cancer model, we send the samples to Matthias Heichenwälder, who I would like to acknowledge also at the very beginning. And they do these fantastic genetic analysis showing that this is really a genetically unstable tumor, an HCC, because they don't metastasize in our hands, so we have to provide they're malignant. Next question we ask, is it really necroptosis? Because RIP kinase 3 claimed to be many other things. MLKL, is it only necroptosis? Is it something else we're doing? So then, Michael, we discussed we have to make the triple knockouts. This is how we approach it. We need the genetic proof that it's necroptosis. So we generate RIP kinase 3 triple knockouts, MLKL triple knockouts, and RIP kinase 1 triple knockouts. 2 years. And then complete rescue. Complete rescue. It is necroptosis, nothing else, that triggers cancer in these livers. So we're back at the question, why is it these two different phases of necroptosis, preventing cancer or activating cancer? Any idea? I already told you the solution. So the two, they don't only suppress necroptosis, right, but they also modify NF-κB. I told you in the beginning here. So in one case, NF-κB is blocked in the TAC1 mice, and in the other way, NF-κB is active. So would NF-κB be the deciding factor here? Again, we need the proof. We need the triple knockouts. And we need, again, not only the IKK subunits, but we also need NF-κB itself, because IKKs are known to do many things. Another 2 years. We're really switching the phenotype through NF-κB. We're coming from this massive infiltration, and here, no single tumor, black and white, and then we see these unreactive necrosis patches again. So it is NF-κB, our old friend from the old days, determines the carcinogenic potential of necroptosis in the liver. How does NF-κB mediate this? So we hypothesized that a dying hepatocyte, it needs to be something in the hepatocytes, because we work with the Cree mice, right? So the phenotype must come from the hepatocytes. So we hypothesized a hepatocyte that dies, upon dying would release these dumps. So maybe NF-κB dependent dumps are crucial. So if you don't, the NF-κB drives the transcription, and the hypothesis was that, okay, the liver cell is full of these factors, but then you need the necroptosis machinery to release them to the surrounding. If you block transcription or MLKL, you would prevent it. And this is what we had done in vivo, right? And I'm only showing here the cell culture experiment. In this case, we decided we go to cell culture. We measure transcription. One is a classical NF-κB dependent chemokinase CCL20, which of course in this case we did an array and we were looking for the top candidates in primary cells, and CCL20 was the top candidate. Transcription follows NF-κB. So in the TRAF2 caspase-8 mice, transcription is high because NF-κB is high. When we block NF-κB, transcription is low. And when we have the RIP kinase 3 mice, this does not affect the transcription. So NF-κB drives transcription. But if we then look in the supernatants, the release, look here, transcription on, but release is off. So kind of supporting our hypothesis that NF-κB and necroptosis work together to drive inflammation through this mechanism. And then we thought, okay, fine, we have it. Let's publish it. And that was in 2016, 6 years ago. We had it under review, and we had one referee who was saying, look, guys, fantastic story, but I don't like a cell death paper without showing me the cell death. Show me that these cells are really dying here. Is necroptosis killing the cells or is it not? And we had no chance to address this question for 4 years. We kept it in the desk with a little level of depression, Michael and me, because we thought we have a great story, but we don't want to give it away, We want to understand what's happening. And then I go here briefly. I forgot to show you that the NF-κB dependent cytokines, we did single cell, we trigger this. We trigger specific macrophages, we even showed in single cell analysis. And these macrophages are pro-fibrogenic and pro-carcinogenic. So it's everything we thought was set, but the referee said, please show me this. Show me death. And then we met somebody who helped us on a day like this. We had a guest in Aachen who wanted to show his research, but said, show me your research. And we said, look, we have this story, and we cannot show the cell death. And he said, I can show it. And the method he was introducing to us is 2-photon imaging. He said, let's film the cells. Let's look at them in vivo in the liver to understand if the cells are dying or not. So this is Jan Hengst and Ahmed Galab. They are both from Dortmund. And Jan said he can even pick up single cells in the liver, single cell death events, because they look for 8 hours, they scan the whole liver. It's fantastic. I'm showing you now the results, comprising also the first movie of a necroptotic cell ever done in vivo. Most people did it in cell culture, but in vivo it has not been shown so far. So we work with 2 things here. We are using a dye that is measuring mitochondrial potential. So if the cell is alive, it's green. If it's dead, it's black. And then we use a second dye. You can, in this case, this Höchst PI staining that is indicating if a membrane is leaky or not. Because the dye has a certain size and it cannot penetrate the membrane, but if you have holes in the membrane, then it can penetrate through. And in this case, it goes directly to the nucleus. So if a cell is leaky, it's pink. The nucleus is pink. If it's intact, it's blue. On the left side of the movie, there is these IKK2 triple knockouts, which these patches, remember? And there you really see that these cells are collapsing in necroptosis. On the right side, there is the cells or the livers, these TRAF2 caspase 8 mice, where we wanted to really show if the cells are dying or not. So this is necroptosis, collapse, IKK2 knockout mice, triple knockouts. And this is how necroptosis looks. Black and leaky, very simultaneous, right? They get leaky and this immediately get black. Here, look at these cells here. Green, alive, but leaky. So, and these stay here for the whole time. See? Leaky. It should die, right? It doesn't want to die. It stays alive. It's a sublethal form of necroptosis. Remember here, these cells die and don't get any cancer. These cells stay alive. We made this Kaplan-Meier analysis of cell death in vivo. I find this fantastic. So they counted these cells. This is the kinetics of necroptosis when it's fully executed. It's very fast. All cells die within 60 minutes. And here, this is these zombie cells. They are undead. And they are the dangerous ones in the liver. Because this cell, I mean, this is really kind of a paradigmatic switch. In this case, cell death, when fully executed, prevents cancer. It's fast, it's rapid, you know, it's like you chop somebody's head off. Whereas here, sublethal injury, you struggle somebody for hours yelling around and the police will come and a lot of immune cells will come and trigger, remember the single cell analysis, trigger fibrosis and trigger cancer. So I'm coming, these are my last 3 or 4 slides. I'm a bit faster but because this has many implications. The question would be, what happens there in these zombie cells? Why don't they die? And there's a very nice paper. I went to another meeting, you know, when I go to meetings, because I don't have maybe enough time to read papers, I saw this guy's paper here, young group leader who published in Developmental Cell a paper on sensing plasma membrane pore formation in survivors of regulated necrosis, a paper about survivors of regulated necrosis, and he was writing, reduction in RIP kinase 3 expression often occurs during tumor growth. It is possible that in late-stage tumors, MLKL is only partially phosphorylated. So if you have very few RIP kinase 3 molecules in a cell, you get very little MLKL phosphorylation. So maybe you get few pores in the membrane, not the whole cell membrane. And then there's he calls it the membrane repair response. Here, you can't see it here. There is a membrane repair response of these sublethal cells that is dependent on TAC1, IKKs, NF-κBs, and chemokines. So he saw what we saw about a year before in a cell culture system, and he was thinking it happens in tumors, because tumors tend to downregulate RIP kinase 3. Remember, we discussed the HepG2 cells. They metallate the promoter. They want to escape death. Now there is a physiological tumor in the body with very little RIP kinase 3 expression, and that is the liver. Look, this is hepatocytes here, and these are cholangiocytes. Cholangiocytes express a lot of RIP kinase 3, but hepatocytes do not express RIP kinase 3, very, very little. They're not free of it, but it's very little. And we believe that is the reason why we get sublethal necroptosis in hepatocytes, but in no other organ. Necroptosis doesn't make cancer in gut, because gut epithelium is extremely high in RIP kinase 3. It doesn't make it in the skin. So this is the last experiment we did. I asked Michael, come on, I need one more breeding. Which breeding do we need? When you look at this one here. Huh? MLKL, yeah? Or which cell should we breed to prove we should delete it in cholangiocytes? Cholangiocytes are high in RIP kinase 3. And if our hypothesis is true, then when we take out TRAF2 and caspase-8 from these cells, we would see these necrosis patches, this unreactive form of cell death. So we crossed TRAF2, caspase-8 mice to SAX9 Cre-ERT mice, and here is the result. It's true. Low expression of RIP kinase 3. So, okay, this is my summary. I'm finished now. You know, like NF-κB determines the execution of MLKL. Rapid lethal necroptosis of hepatocytes or cholangiocytes is non-immunogenic. It prevents cancer. Sublethal MLKA activation collaborates with NF-κB to trigger hepatocellular carcinoma. Low RIP kinase 3 expression can be more dangerous than high RIP kinase 3 expression, and beware of zombie cells. I would like to show you one more unpublished finding. How can we use this as a therapy? We thought, let's try it in pancreatic cancer. and ductal cells might be high in RIP kinase 3. And in fact, this looks very, very promising. We can completely prevent pancreatic cancer, and we can also treat human organates when we activate RIP kinase 3 signaling in these cells. So with this, I would like to finish this. I would like to again acknowledge the work of Michael mainly and Anne Schneider, and also the collaboration partners, like the many we have on our paper. We have 46 authors. This is 12 years of work. Not all our stories take 12 years. It's very important for me to say this. We have also other stories, but I would like to acknowledge, of course, Matthias, that worked with me, Thomas, with Javier, we're working together, Jan Hengstler with the 2-photon, Frank, Derek, and we have some human data also that I didn't show with Augusto, that the pathway seems to be active in human HCC. And with this is now the group we're working in Düsseldorf. If you like, follow me on Twitter. And thanks again, and I'm looking forward to discussion. We downregulated RIP kinase 3 with siRNA in these cells, and then we used NF-κB inhibitors, and in fact we saw now a dependency of cell death execution timing when we block NF-κB. So we can also now have a cellular system that is enabling us to study it, but we don't have yet a clear answer how NF-κB makes this dramatic switch. Here we used only mice that are black or white. In the cell culture system, we could also kind of reproduce it with using inhibitors, chemical inhibitors. But it's a very good point that I'm taking home. It might be good to make kind of a dose dependency of NF-κB function to identify the switch between the two, right? So that's a very good idea. Other cell death pathways. So does it interact with other cell death pathways? RIP kinase 1, for example. I think there was a recent paper on a TAC1 knockout mouse claiming that there's ferroptosis in this pathway. So in our hands, there's no direct interaction between necroptosis and pyroptosis. There's also a very fresh paper out there claiming that there is no pyroptotic cell death in hepatocytes. That came out just a couple of days ago. I cannot exclude it though. We have an indication that TAC1 might signal towards pyroptosis, and it's interesting. Please remember, when we take out the downstream mediators, MLKL for example, which is clearly independent of ferroptosis, we completely rescue. So this argues against a major function of other, like pyroptosis.
Opinion.
Yes, sorry, I was jumping a bit over these single cell data. I apologize for this. It's mainly monocytes. Monocyte macrophages, MOMF, this, like the monocyte macrophage population. There is a clearly distinct population of monocytes, and that's the cool thing about this single cell analysis, that there's also macrophages in the hyporeactive form that only surround these granuloma-like patches, but they are completely unreactive. Also, you see it on the transcription level in the monocytes. So there we have a very highly reactive monocyte subpopulation expressing these pro-fibrogenic and pro-carcinogenic genes. They activate the stellate cells. They probably trigger also the proliferation. So monocyte macrophages respond very actively towards this hypernecroptosis. No, I don't know, and that's a very interesting point. that we have not really addressed. Why can they stay alive? You know, I mean, the point that I learned from this, or I thought about, you know, we have in the liver Kupffer cells and hepatocytes. And the Kupffer cells are the natural secretors. They have a really secretion machinery to secrete TNF and IL-6 and some. Hepatocytes normally, I think, do not really have an active shedding and secretion machine. They're normally not so much producing chemokines unless, you know, you make these MLKL pores into the membrane and where they then have a release mechanism. And if a hepatocyte can do that, you get this obscure inflammatory phenotype when you activate their machinery that normally is probably not there. So that was my conclusion, Kupffer cells versus hepatocytes and what this MLKL machinery could do. Yeah, but it's important to understand why they're not phagocytic. We can look in the two-photon analysis. If you look along, you see the monocytes running around, you know, and they're not, you're right, they're not eating up. Whereas in the other one, they do that. They come and they phagocytize the. So it must be an NF-κB-dependent non-eat me signal that could be found in this model. Very good point, yes. So I mean, the FIB4 score is a score that was established by the big consortia in NAFLD. And they did an unbiased search, what are the highly predictive information that you get from a normal patient score to predict progression towards fibrosis. And there they identified this score. And we noticed that 2 of the 4 main markers are cell death. One is age, maybe senescence, and one is platelets, liver function, you know, or platelets. They might be more to platelets, and so this is why we believe that cell death is very nicely reflected in the FIB4 score. But the FIB4 score is normally used not to predict, you know, like in late stage, because like a late stage person has a FIB4 score of 25 and more, you know. It's nice though, I thank you very much for this question, because now people are looking for FIB4 in many settings. You could look in your myocardial infarction patients, does FIB4 predict bad prognosis? In corona, I said, let's look in the corona patients, already 6 papers out, you know, like when we even thought about it. So there might be also a role of FIB4. I don't know if you caught your question right, in the later points. And thank you for one important point I want to mention here. In the FIB4, AST is above the thing, and ALT is below. We believe ALT is rather an apoptosis marker and AST rather a necrosis marker. So this would mean the more necrosis you have, the worse is your score. Apoptosis would be better in this case. ALT is better, so the ratio of AST to ALT would imply maybe if necrosis goes on, it's specifically bad. So that's a very simplistic way that I try to address your question. For this question, there is tons of companies and papers, whole journals that are studying how can we augment anti-immunity in immuno-checkpoint therapy of tumors. That's the billion-dollar question, right? Make the tumor hot. That's the label of the companies. And many people thought, let's activate programmed cell death. And I was skipping that part because of time reasons. We believe that with the pro-apoptotic regulation, like you see in Nemo mice, you can augment it. But in programmed cell death, at least necroptosis, we believe execution of necroptosis is not a good way to trigger immunity. That's our data, what they show. And there is a group, Peter van den Abilis group, he's one of the popes of cell death, you know, and he showed the same for ferroptosis. He says no. ferroptosis does not trigger or augment an an anti-tumor response. But the sublethal necroptosis, maybe we want to trigger it in cancer patients to boost anti-inflammatory responses. We have not specifically looked at T-cell responses in our mice, which would be an interesting, and we're working currently on that. So next time I come, I can hopefully show this.
Perfect.
Thanks, Joanna. So I am again going back to this question, and maybe it was jumping a bit. I should have shown the data. So the referee said, look, and also when I went to a big conference, one guy said to me, look, we have been working on necroptosis for 15 years, and we have never seen a dependency of NF-κB and necroptosis. There must be something wrong with these data. So we thought, okay, what could be the reason? And we believe, then we said, it's only true when RIP kinase 3 is very low expressed in cells. Remember, low RIP kinase 3, very little MLK-alpha phosphorylation, probably very few pores, sublethal. So in the cell systems like L929, when you trigger necroptosis, they are full of RIP kinase 3. It was discovered in these cells. They immediately undergo necroptosis. You put TNF on these cells, rapid necroptosis. And we thought, okay, if it's true that you need little RIP kinase 3 expression to see the relation between NF-κB and necroptosis, we have to silence RIP kinase 3 expression in L929 cells. And then we would see that if we inhibit NF-κB, cell death is faster. And in fact, we could show this. We didn't publish this finding. We want this to be confirmed by another group first. And we have one confirmation we have already. So if Dr. Gonzalez, I guess, if you have anything done in this direction, let us know if you see the same thing. I mean, it's a funny question, really. No, it's a perfect question. It's a funny situation. Sorry, it's not a funny question. I misspelled it. It's a very good question, and it's a funny thing in the liver. This is what I wanted to say. When I went to med school, I learned apoptosis is an unreactive cell death form, right? Happening during development, and necrosis is very reactive. We believe apoptosis can be very reactive in the liver. Mm-hmm. And this riddle is not really solved, right? Why is apoptosis in the liver? Is there secondary necrosis going on? But we are trying to define the apoptome versus the necroptome. And what we're seeing is that the alarmine signatures, the dump signatures of apoptosis versus necroptosis are completely different. So, for example, HMGB1 is a classical alarmine that we did not see in the necroptosis, but that's very active or very much released in apoptotic cell death. So there is, I mean, the Nemo mouse is a hyper-reactive apoptosis mouse that Javier and I worked with a lot of for a long time, and it's a nice study. So what we to summarize this question, we define in the mouse models which factors are released from apoptosis or necroptosis, and then we want to go to the patients and see if we can see these signatures in certain diseases in the blood, maybe even. If we cannot do 2-photon in patients, of course, but maybe we can define the cell death forms by looking at the signatures. Mm-hmm. You know? And I thank you very much for this question. Questions? Yes, it could be done. We know that RIP kinase 3 expression is controlled by epigenetic mechanism, by methylation. Mm-hmm. You know, so in cell culture systems, you can use a methylation inhibitor. You re-establish RIP kinase 3 expression, and then we believe, and there's data from this paper. It's published about 8 years ago in, I think, Oncogene or so, that then liver cells can be sensitive to conventional chemotherapy. You know, the question is why do they not respond to chemotherapy? And re-establishing expression of RIP kinase 3 might indeed trigger this. So it might be possible. I think you cannot treat a patient with a PAN methylation inhibitor.
Yes.
I don't know if in some cancers that happens. This could be in fact a way. I cannot really tell you. I think they like, you have to distinguish between the way towards cancer and then the cancer itself. I think the cancers themselves like losing RIP kinase 3 expression at some point because they want to escape death, right? It's a natural selection process. But for example, in the gut epithelium, we know that necroptosis can be activated, and we never heard of a cancer arising from gut epithelium. So on the way towards cancer, it's protective.
Okay.
Yes. So thanks again. I mean, you know, you are summarizing kind of what I wanted to show. We also believe that hepatocytes do not die by necroptosis. We have never checked if they can still release AST from these pores, maybe without death. You know, we have to rethink if we measure cell death. But we measured RIP kinase 3 expression in phospho-MLKL. I showed the plot here very briefly on the right side from primary hepatocytes. And they upregulate RIP kinase 3 a bit, the TRAF2 caspase 8 mice, and yes, they can phosphorylate MLKL. So we believe you can activate the signaling. It's very difficult to catch it by Western blot. That's why I said you have showed very nice plots where you're trying to show the pathway, but it's difficult.
Yes, it is.
You know, to see it in hepatocytes. And but you can trigger the signaling, and the question is now, can we find the zombie cells in human NASH patients? You know, Ahmed and Jan did one experiment where they saw, at least in cell culture of human cells, that you can have them. How can you transfer to photon into patients, maybe with MRI or with some PET? This is something we want to develop work on with Jan, maybe also with this model in the future.
Precision liver slices, maybe?
Yeah. We have now bought this machine and went to Newcastle to learn it.
To Derek.
To Derek, and let's see if they can do it.
Okay, I think it's time to finish. So thank you very much, Tom, for this excellent talk, and thank you to the rest of the audience that were here. And we hope that you enjoyed these Levy seminars like we did really enjoy it. So, and see you next time. Thank you.